Okay, so this is the first AP FRQ review for stats, and I'm going to go over questions from 2017 number 3, 2016 number 6 parts A and B, 2011 number 3, and 2013 number 5. So let's start with 2017 number 3. A grocery store purchases melons from two distributors J and K. Distributor J provides melons from organic farms. The distribution of the diameters of the melons from distributor J is approximately normal with a mean of 133 millimeters and standard deviation 5 millimeters. Part A, for a melon selected at random from distributor J, what is the probability that the melon will have a diameter greater than 137 millimeters? So this is a garden variety normal distribution problem. So you want to find the probability that you will get a single melon, let's call that X, with a diameter more than 137. You convert that to a z-score, so 137 minus 133 over 5. And you want to know the probability of getting a z-score greater than 0.8, which is the 137 millimeter wide melon. That corresponds to a probability of 0.2119. So you can use normal CDF with the area greater than 137 with a mean of 133 and a standard deviation of 5. Part B, distributor K provides melons from non-organic farms. The probability is 0.8413 that a melon selected at random from distributor K will have a diameter greater than 137 millimeters. For all the melons at the grocery store, 70% of the melons are provided by J and 30% are provided by K. So for a melon selected at random from a grocery store, what is the probability that the melon will have a diameter greater than 137 millimeters? So you're looking at the melons that are from both distributors J and K. So you want to draw a tree diagram. The first decision point is where the melon came from. There's a 0.7 chance it came from J and a 0.3 chance that it came from K. Next, you want to know whether the melon is going to be greater than 137 millimeters in diameter. So for distributor J, the answer to part A told you it was 0.2119, that would be wider than 137 millimeters in diameter. For distributor K, it would be 0.8413 as given in the problem. Now you want to look at the outcomes where the melons have a diameter greater than 137. So you're going to multiply 0.7 times 0.2119, those are the melons from J, and then 0.3 times 0.8413, those are the melons from K. And you're going to add up these two probabilities to get a total probability of 0.4007. So of the 4 outcomes, 2 of them end up with melons wider than 137 millimeters diameter. You want to take each of those events, multiply the probabilities along the tree diagram, and add them up. C, given that a melon selected at random from the grocery store has a diameter greater than 137, what is the probability that the melon will be from distributor J? So this is a conditional probability where the probability that it's coming from J, given that it's 137 millimeters, is equal to the probability of both events happening divided by the probability that the condition happens. So both events being the probability that J and 137 divided by the probability of 137. So the probability of both being from J and 137 is 0.1483. You would multiply the 0.7 times the 0.2119, and you would divide that by the probability that you calculated in part B, the probability that any melon from any distributor is wider than 137 millimeters, and that gets you a conditional probability of 0.3702, which means if you know that the melon has a diameter more than 137 millimeters, there's a 0.3702 likelihood that it came from distributor J. Next, let's look at number 6 from 2016. We're only looking at the first 2 parts. A newspaper in Germany reported that the more semesters needed to complete an academic program at a university, the greater the starting salary in the first year of a job. The report was based on a study that used a random sample of 24 people who had recently completed an academic program. Information was collected on the number of semesters each person in the sample needed to complete the program and the starting salary in thousands of euros for the first year of a job. The data are shown in the scatter plot below. So part A asks, does the scatter plot support the newspaper report about number of semesters and starting salary? Justify your answer. And as you can see, generally speaking, the answer is yes. There's a positive relationship between the number of semesters needed to study to complete the degree and the starting salary. In other words, the higher the number of semesters completed, starting salary does tend to increase. So there does appear to be a positive relationship. B, the table below shows computer output from a linear regression analysis on the data. Identify the slope of the least squares regression line and interpret the slope in context. So here's the data printout that you might want to familiarize yourself with again. And the number that you want to look at is the coefficient for the x variable, the explanatory variable, which is semesters. So the slope is 1.1594. Now remember, to interpret the slope, it's the average predicted change in y for a change of 1 unit of x. So in this case, it would be on average for each additional semester of study needed to complete an academic program at this university in Germany, we predict that the starting salary will increase by 1.1594 thousands of euros, or 1,159.40 euros. So don't forget that it's a prediction, it's on average, and then you're looking at the change in y for each unit change in x. Number 3 from 2011, apartment building has 9 floors and each floor has 4 apartments. The building owner wants to install new carpeting in 8 apartments to see how well it wears before she decides whether to replace the carpet in the entire building. So here's the diagram. The figure below shows the floors of apartments in the building with their apartment numbers. Only the 9 apartments indicated with an asterisk have children in the apartment. Part A, for convenience, the apartment building owner wants to use a cluster sampling method in which the floors are clusters to select the 8 apartments. Describe a process for randomly selecting 8 different apartments using this method. So if you recall, a cluster sample is when you randomly select from all groups and then you take every member in the randomly selected group. So in this case, the owner can use a random number generator to generate 2 unique numbers from 1 to 9, where each number corresponds to the floor. Once the owner selects those 2 numbers, the owner will include all 4 apartments of the 2 selected floors to make up the sample of 8 different apartments. So for example, if the owner selects randomly selects the 3rd floor and the 5th floor, she will take everyone in the 3rd floor, which is apartments 31, 32, 33, and 34, and everyone on the 5th floor, which is 51, 52, 53, and 54. Part B, an alternative sampling method would be to select a stratified random sample of 8 apartments, where the strata are apartments with children and apartments with no children. A stratified random sample of size 8 might include 2 randomly selected apartments with children and 6 randomly selected apartments with no children. In the context of this situation, give one statistical advantage of selecting such a stratified sample as opposed to a cluster sample of 8 apartments using the floor as clusters. So one reason for doing a stratified sample is that you believe that there's going to be a significant difference between the carpet wear in apartments with children versus without. So for example, apartments with children may wear out carpet at a different rate than apartments without, because children run around. Maybe that the carpet in children apartments will wear out faster. So since there are 9 apartments with children out of 36, we want 2 apartments with children to be part of the sample of 8. So the owner can stratify the apartments by whether there are children and randomly select from both groups and combine them. So this ensures that both types of apartments are represented in the sample. So you would choose 2 of the 9 apartments with children, randomly choose those 2, and among the other 27 apartments without children, you would take 6 and you would combine those 2 apartments with children and 6 apartments without children to make up the 8 apartment sample. Finally, let's look at 2013 number 5. Psychologists interested in the relationship between meditation and health conducted a study with a random sample of 28 men who live in a large retirement community. Of the men in the sample, 11 reported that they participate in daily meditation and 17 reported that they do not. The researchers wanted to perform a hypothesis test of H0 being PM minus PC equals 0 and alternative PM minus PC is less than 0, where PM is the proportion of men with high blood pressure among the men in the retirement community who participate in daily meditation, and PC is the proportion of men with high blood pressure among all the men in the retirement community who do not participate in daily meditation. Part A, if the study were to provide significant evidence against the null in favor of the alternative, would it be reasonable for the psychologist to conclude that daily meditation causes a reduction in blood pressure for men in the retirement community? Why or why not? So the big question here is causation. And because this was an observational study, it was not a controlled experiment, and without the fact it being a controlled experiment, you cannot conclude a cause and effect relationship. So there might be other reasons that cause or contribute to the reduction of blood pressure aside from daily meditation. So you can only conclude causation from a controlled experiment, not from a mere observational study. B, the psychologist found that of the 11 men in the study who participate in daily meditation, 0 had high blood pressure. Of the 17 men who do not participate in daily meditation, 8 had high blood pressure. So let PM hat represent the proportion of men with high blood pressure among those in a random sample of 11 who meditate daily, and let PC hat represent the proportion of men with high blood pressure among those in a random sample of 17 who do not meditate daily. Why is it not reasonable to use a normal approximation for the sampling distribution of PM hat minus PC hat? So this is a question that I could see them asking on this abbreviated AP test. It doesn't require a calculator to do it, and yet you still need to check the normal condition. So in this case, to use the normal approximation, there must be at least 10 people in each sample with high blood pressure and 10 people in each sample without. So that's the N1 P1 hat, N11 minus P1 hat, N2 P2 hat, and N21 minus P2 hat. All 4 of those values have to be at least 10. So at least 10 successes and 10 failures in both samples. Now in this case, the meditation group had 0 with high blood pressure. Well, that's less than 10. The non-meditation group had only 8 with high blood pressure and 9 without. So 3 of the 4 quantities are not at least 10. So the normal condition is not usable because your sample size is too small. Part C, again, this is a question I could see them asking using these simulations, because if you can't use a calculator, or you can use a calculator, but if they tell you that the calculator isn't needed, they might give you something like this. Although a normal approximation cannot be used, it is possible to simulate the distribution of PM hat minus PC hat. Under the assumption that the null hypothesis is true, 10,000 values of PM hat minus PC hat were simulated. The histogram below shows the results of the simulation. So part C asks, based on the results of the simulation, what can be concluded about the relationship between blood pressure and meditation among men in the retirement community? So what you wanted to do is take your observed PM hat, which is the percentage of those that got high blood pressure that meditate, and subtract the percentage or proportion of those that don't meditate that end up with high blood pressure, that's P hat C. So in the meditation group, 0 out of 11 had high blood pressure. In the non-meditation group, 8 out of 17 had high blood pressure, and if you take those differences, you get a difference of negative 0.47. Now if you take a look at the histogram, this difference, or difference greater than this, in this case would be less than negative 0.47, only took place 76 times out of the 10,000 trials. So what this means is it's an effective p-value of 76 over 10,000, or 0.0076. So instead of using a table to calculate a p-value or using stat tests, you might be given a histogram where you're going to have to interpret the histogram. And again, the p-value is the probability that you will get a value as extreme or more extreme than what you observed, given that the null hypothesis is true. So you're told that in these simulations, the null hypothesis is true. If that's the case, only 76 times out of 10,000 did you get a difference of negative 0.47 or less. So since this value is less than 0.05, you would say that this difference was unlikely to have happened strictly by chance. So there's convincing evidence that the men in this retirement community who meditate were less likely to have high blood pressure compared to those who don't meditate. But again, as you mentioned in part A, because this is an observational study, you cannot conclude that meditation decreases the likelihood of high blood pressure. All you can say is there is a relationship between meditation and lower incidence of high blood pressure. So that's it for these first set of AP FRQs. If you have any questions, please feel free to email me or join in the office hours. I'll be happy to go over any questions you have.